Hello, my name is Wes Furmanek. I'm a current senior in material science and engineering, and today I'll be presenting my honors capstone project entitled Photo Assisted Flow Battery Charging. So the way I got involved with this project is through a course in my minor in energy science and policy. Uh, the course was ME 433 Advanced Energy Solutions, and Professor Quabi was actually the instructor for that course. And during the course, he talked about some of his research in flow batteries and energy storage, and I found it really interesting. So I approached him and told him about how I was looking for an honors capstone project and would like to work in his lab. And he graciously presented the idea for this project, which I took from just an idea. And as I'll tell you here in a few minutes, I took it all the way through to a project that will continue on past my work on it. So a little bit of background. One of the big problems with some renewable energy sources, and specifically solar energy, is that they don't always generate when you want to use the energy from them. So, for example, with solar energy, you're only able to get energy from it when you have sunlight, and the sun obviously doesn't shine all the time. So, to get that energy when you want it, you have to couple it with an energy storage system so that you can draw it when you need that energy. But this coupling of these energy storage and solar systems have efficiency losses because you have these connections that you have to connect the two individual systems, and those connections also take up a greater amount of space. So a potential solution to cut down on those losses is the integration of a type of solar cell known as a dye-sensitized solar cell with a battery known as a redox flow battery. So they're two kind of specific types of solar cells and batteries respectively. And the combination of these two are what's known as solar flow batteries. So this diagram over here on the right kind of shows the structure of a solar flow battery. There's a lot going on, but some of the main things to look at are the photoelectrode here, which is basically the dye-sensitized solar cell where you're collecting that sunlight and generating energy from it. And then these two large areas of analyte and catholyte. Basically what those are, they're electrolytes, which are water solution with ions dissolved in them. And those ions are what take place in what are known as oxidation reduction reactions, which are reactions which happen in one direction when you're charging the battery and the other direction when you're discharging the battery. And both the dye-sensitized solar cells and redox flow batteries need a lot of electrolyte. So the combination of these two really allows you to utilize that commonality. And because of the way this structure can be integrated, you cut down on your space losses and on some of these efficiency losses because it's a really direct integration as opposed to using like wiring and other connection. So the work that I did was actually producing these photoanodes or the solar cells. So this process starts out with formulating the paste. So there's a paste of titanium dioxide, which you disperse onto a conductive glass slide. So here's an uncoated slide, then coated with the paste, and then you go through and you dry that paste at a high temperature, and then you go through and sensitize these pastes with the dye solution. And that's basically just taking this coated and dried sample and soaking into a solution of dye molecules. And those dye molecules are collected within the structure of that paste, and those dye molecules are very important because that's what actually is absorbing the sunlight and generating electrons to store in your battery. And here's a little video of what the actual paste dispersion looks like, so you can see it being dragged across the glass. And then after this, I went through and tested the photoanodes in a type of testing known as cyclic voltammetry, where you apply voltages to the photoanode and you measure the current response in light and dark to kind of see what amount of energy you're generating. So here are some of the main testing results. I tested 4 different samples at 4 different sensitization times, trying to isolate the effect of the amount of time you're sensitizing towards to correlate it kind of towards your power production. And you can see the S2 sample, it was normalized so that it was operating on the same area amount, so that all of these samples are utilizing the same surface area for electricity production. And you can see that there is some correlation between the amount of power you're able to produce with the sensitization times, but the biggest takeaway from this for me is that the power production is lower than what I'd really be hoping to get, almost on the scale of like 5 to 10 times lower than what we'd be hoping to get. So there's good and bad news. Good news is that as a proof of concept, this is working. Like clearly there's power production under the sunlight, which is means that the solar cells are operating as solar cells, which is great news, but it is far from an optimized process. So there's a lot of work that still needs to be done. So to look at why I wasn't getting such great performance from these, I went through and did scanning electron microscopy, or SEM, which allows you to really look in on the small scale at the structure of the photoanodes. So on the left, you can see the structure of a photoanode before it is heat treated and sensitized, and then you can see after the heat treat on the right. And there's clearly a great difference between the two. So prior to the heat treat, you have this very rough, kind of crystalline and pointy structure with a lot of flat faces. And then after the heat treat, you have this very porous and interconnected, very high surface area structure, which is really what we're looking for because the reactions that drive the generation of electricity happen at the surface of the photoelectrode. So if we have more surface area, we can have more reactions taking place and generating more electricity. So this kind of tells us that this is surface area is not necessarily the issue that we're looking at here. And that was the extent of my experimental data collection so far. So there's a lot of work left to be done, as I had mentioned. And though I'm a graduating senior, I actually will be continuing to work on this throughout the summer. I'll be coming back for a master's degree in energy systems engineering, and Professor Kwabi has allowed me to keep working throughout the summer. So this future work is not just a general, but actually future work that I will be doing. So the photoanode production process needs to be refined a little bit. I need to finalize some of the paste formulation and dispersion, and then determine what parameters really affect the performance the most. So that'll be a very iterative process. Then I'll go through and characterize the photoanode in similar ways that I mentioned previously, look at the surface structure as well as the electronic or electrical properties, then going through and implementing it into an actual flow cell or a flow battery. So this can be seen over here on the right in this picture. This little square here is actually where the sunlight or light would be shown onto the photoanode. And then these tubes are what are cycling through the electrolyte into one side of the cell, out, and then pumped back through to the other side and really running the flow cell. So testing that under an actual light source would give us a great idea of what kind of performance we would get for the total setup. So that's the bulk of my presentation. I just want to give a couple of acknowledgments here for people who've helped me along the way. Most notably, Professor Kwabi. He really helped me out by, first of all, just being gracious enough to allow me to work on this project and has helped me every step of the way and been a great contact and a great mentor for me. Some of the graduate students in the Kwabi lab, Sanat, helped me with a lot of my experimental design, and Jansu really helped design the flow cell that we just saw in that last slide. So thank you to both of them. Also, thank you to those in the Professor Zetian Mee's lab. Professor Mee's lab has the light source that I was using to test, and Arthur, one of his PhD students, had trained me on that, as well as Dr. Pilar Herrera Fierro, who helped train me on using the scanning electron microscope, as well as helping me to take some of those images. And of course, the College of Engineering honor staff who helped me kind of come up with ideas for projects and, been a source of contact and mentorship throughout all the way from my sophomore year and even through now to graduating and being a senior. So thank you to all of those. I really hope that you're able to take something away from this. And if you have any questions or comments, please leave them in the comment section below and I'll do my best to answer them. Thank you.